All right, so let's look at the last process in making urine, and that is tubular secretion. So this is a process of substances moving out of the peritubular capillaries and into the renal tubule. So we're moving stuff out of the peritubular capillaries into the renal tubule to get into the urine. So, this is one of the ways that we can get rid of stuff, substances not already in the filtrate. So getting rid of metabolic waste such as urea, uric acid, certain drugs, and creatinine. All right. We can also get rid of excess potassium ions this way. This is also one of the ways in which we can help control our body's pH. So we can secrete hydrogen ions, and so that's going to make urine acidic, or we can secrete bicarbonate ions, and that's less common to make the urine basic, but that's not as common. We mainly get rid of hydrogen ions here. So those were the three processes in making urine. So glomerular filtration, tubular reabsorption, and then tubular secretion. All right, so now let's look at the regulation of urine concentration and volume. So getting to this process. So one of the things that we're going to look at here is what is known as osmolality. And this is a number of dissolved in 1 liter of water. And it reflects the concentration of the solution's ability to cause osmosis, whether water is going to shift from one fluid into another fluid. All right? So an osmol is 1 mole of non-ionizing substances per liter of water. And a milliosmol is the solid concentration of bodily fluids. That's what we're looking at, milliosmols. So our solid concentration in our plasma is about 300 milliosmol. And so what we're going to look at is what is known as a countercurrent mechanism. And this is used to keep solid loads of the blood and the urine to about 300 milliosmols. So what we mean by the countercurrent mechanism is this is showing the loop of Henle here, and this is showing the blood flow in the vasa recta. As you can see, the arrows here going in the opposite of the arrows in the vasa recta. All right, and this is used to vary that urine concentration. So let's look more specifically at that countercurrent multiplier. So if we look at the descending limb of the loop of Henle over here, this limb is relatively impermeable to solids, but it's freely permeable to water. So water is going to leave the filtrate here by osmosis back into the blood. All right? And so when it does so, by water leaving here, the solid concentrations start getting more and more concentrated. So about 1,200 milliosmol right there at the elbow or the bend there in the loop of Henle. Now if we look at the ascending limb of the loop of Henle, so over here, this limb is permeable to solids. So you can see these different ions there, but it's not permeable to water. So water cannot move through there. All right? So here, this is where sodium, and you can see potassium and chloride ions, those are reabsorbed there. And so here, the filtrate can become very dilute. All right? And so by the distal convoluted tubule there, it's about 100 milliosmol. All right? And so if we think about this, what we do here is we reabsorb a lot of solids on this side of the vasa recta, and then by the time the vasa recta gets over here, the blood solid concentration is pretty high, and so because it's pretty high here, it can absorb a lot of water on the descending limb of the loop of Henle. Now if we look back into the urine, all right, so if we have dilute urine, so here no antidiuretic hormone is released, and so here the collecting ducts are impermeable to water. All right, so this would just stay at 100. These increasing numbers aren't showing this properly. But if no ADH is secreted, the urine concentrations will stay at 100. If we make a concentrated urine, and that's what this is trying to show here, so we secrete antidiuretic hormone. All right, and so what's going to happen there is the aquaporins in the distal convoluted tubule and collecting duct are going to open up. We're going to reabsorb more water back into the blood.